Hello everybody, welcome to our searching and sorting algorithm series part 1. Today I'm going to explain binary search. Binary search is one of the most efficient algorithms for finding an item in a sorted list. So what is binary search? Binary search is a divide and conquer algorithm. It works by repeatedly dividing a sorted array or list into two halves and eliminating one half based on a comparison. Because binary search compare the element in the middle index to the target value in order to determine which search interval to check. By doing so, it dramatically reduces the number of comparisons needed to find the target element. Therefore, binary search has a time complexity of O of log n, making it much faster than linear search. And the key here is that binary search only works on sorted data. If the array isn't sorted, binary search won't give you the correct results. The algorithm picks the middle element of the array and compares it to the target value. So when the algorithm compares the values, there will be three possible outcomes. So, firstly, if the middle element matches the target, then we are done because we basically found the target that we are looking for. And the next thing is when the middle element is greater than the target. It means the target must be in the left half of the array, so we discard the right half. Lastly, when the middle element is less than the target, it means that the target must be in the right half, so we will discard the left half. Now that we've discussed what binary search is and how it works, let's take a closer look at the key variables that make binary search function. These key variables would be left, mid, right, and target. So first, we need to define the boundaries of our search. So to define the boundaries, we would need the help of two variables called left and right. Basically, left is the starting point of our search, which initially is the index of the first element in the array. Right is the ending point of our search, which initially is the index of the last element in the array. These two variables tell us the range or the slice of the array that we are currently focusing on. At the beginning of the search, left will be at index 0, and right will be the last index. As we continue the search, we will adjust these variables to zoom in on the section where we expect to find the target. The next variable is the target, and it is the value that we are searching for in the array. The goal of binary search is to check if the target exists in the sorted array, and if it does, we will return the index. At each step, we are trying to determine whether the target is in the left half or in the right half of our current searching range, and that is where the next variable comes in. So mid would be the last variable to discuss. Mid will be a variable that keeps track of the middle index of our current search range or the array slice that we are looking at. Back at our example, we can see that our element in the middle index is 5 and the target that we are looking for is 10. When we compare 5 to 10, we can definitely say that we are not going to check the left half of the array. So we will divide or split the array into two halves, and it will result in something like this. Okay, now we can see the array being divided into two halves, the left half and the right half. On the left half, we will have the values that are going to be less than the target that we're looking for. Okay, so moving on, we definitely know that our target won't be in the left half of the array. We will be changing our searching range to the right half of the array. In order to do that, we will have to change the values of left and right. But in our case, left will become the index just after mid, and we can calculate the value of mid by using the new left and right variables. And after that, we will be able to get 4 as the middle index. And we can see that the middle index is also 10, which is equal to our target. And we will be able to return the index or mid, which is 4, therefore ending the binary search process. Here's another example where I will manually perform binary search on this following array. First, we have the middle element, which is 16. When we compare 16 to 4, we can definitely say that we won't be needing to check the right half of the array. We will change the searching range to the left half of the array. In the left half of the array, we will compute the middle element, which will be 8 in this case. We will compare 8 to 4. Since 8 is greater than 4, we won't be needing to check the right half of this searching range. Therefore, we will split or divide it into 2 halves. Lastly, we will have the target that we are looking for. Now I will perform some binary searches on these following arrays. Now that we understand how binary search works, let's talk about an important aspect of any algorithm: time complexity. In simple terms, time complexity tells us how the execution time of an algorithm grows as the size of the input data increases. For the best case, we will have O of 1, meaning its constant time, when the target is located at the middle of the array. For the average case, binary search have a time complexity of O of log n. For the worst case scenario, when the target does not exist or when the target is at the end, we will have O of log n. So we will be explaining more about the big O notation in a separate video, so just make sure you click the bell icon to be notified whenever a new video comes out. Now that we've covered time complexity, let's talk about another important concept: space complexity. While time complexity measures how long an algorithm takes to run, space complexity measures how much extra memory or space the algorithm uses as the size of input increases. Space complexity refers to the amount of memory the algorithm needs to execute. It includes the space required to store the input data, the extra space used by the algorithm to perform its computations. This includes variables, data structures, or anything. an algorithm creates while running. What is the space complexity of binary search? The great thing about binary search is that it's very efficient in terms of space. And this is why. Variables used in binary search are very few, such as left, right, mid, and target. And these simple variables doesn't grow in size as the size of input array grows. Whether you're searching through 10 elements or 1000, you will still need the same number of variables. However, if you're using recursive version of binary search, the space complexity would be O of log n, due to the recursive call stack. Where n is the size of the array, each recursive call consumes additional stack space. We will explain about recursive binary search in our later videos. Now let's start writing our binary search algorithm in our Java code editor. First, we will initialize the variables that are needed, which are left, right, mid. So left would be 0 by default. And right would be the length of the array subtracted by 1. Here will be our main loop, which will run as long as our left is less than or equal to our right index. Next, we will calculate the middle index of our array. We can calculate it by combining left and right and by dividing it by 2. For alternative way, we can also do a math.floorDiff and left plus right 2. We can also do this in order to get the middle index by using the object math. So after getting our value of mid, we can now check if our target is equal to the middle element. If it is, we will return the middle index or the index of our target. So if our target is less than the middle element, we will be checking the left half of the array. Therefore, our right index would be the index just before the mid index. Lastly, left would be the element just after mid, because our last condition would be when the target is greater than the middle element. So we would be checking for the right half of the array. Therefore, we will have to change the value of left. If the desired element or target is not found, we will be returning -1. We will create a brand new array. We will have to make sure that our array is in a sorted order. We will call the binary search method on this new array, and we will search for the value 7. It returns 4. So we will check if it is accurate or not. 0, 1, 2, 3, 4. We have basically found 7 at index 4. Therefore, our binary search algorithm works indeed. Alright, now we've walked through the binary search algorithm and also implemented it in Java. To quickly recap binary search, we can say that binary search is very powerful because it cuts the search space in half with each step, making it much faster than linear search. And its time complexity is O of log n, meaning it scales efficiently even with very large datasets. When binary search is implemented iteratively, the space complexity is O of 1, meaning it only uses a constant amount of extra memory. So that will be it for today, and Next videos, I will dive deeper into big O notation and recursive binary search. So stay tuned for more, and if you have any questions or suggestions, feel free to leave a comment below. Thanks for watching, and see you all in the next one.